Good morning, gentlemen. Today I'm going to discuss more on how to work with CUDA. And although I'm aware that you can install CUDA and make it work natively on Windows machine, if you install the CUDA toolkit in your Windows, and you should be able to directly work with CUDA and Visual Studio. In fact, once you do that, your Visual Studio template will have these additional CUDA. Like if I create a new project here, and down here you'll see the CUDA 12.1 runtime, wherein it will give you an initial setup of a Visual Studio project which is correctly linked to the CUDA headers, CUDA libraries, CUDA paths that you just get installed in your Windows machine. Okay, but the session that I'm going to do here is a little bit different. The CUDA system that I have is in my Jetson, in my remote machine, in my Jetson Nano board. So I'm going to open the project. It's a Linux project, this one. So it's very small, and the intention is how to set up for CUDA, which is not in your Windows. So you will notice the IP here. This is the IP address of the Jetson board. Let me log in there. Now I'm logged in. But first, let us try to observe something here. So this would be the standard CUDA header files, the CUDA_runtime. And while my IDE here is in Windows, take note that when I build this, since this is a remote compilation setup, that's what a Linux project is all about. It's a remote compilation. The Visual Studio is going to use everything in the remote box, in the remote target, to compile. So it will use the compiler there, it will use the file system there, it will use the header there and libraries there. So it's not going to it's going to drop everything in my Windows local machine, and it's going to use everything there. These operations are going to be facilitated by the existing SSH connection that this IDE has established to that remote target. So when I say CUDA runtime.h, this header file CUDA runtime.h is present in that remote target. And if I go to the properties here, and in this configuration, you will notice this user local CUDA include. And from the / format, this is a file system in the Linux machine, and it's not in my Windows path. So I log in here in the remote system. I can go to user local CUDA include, and it would be this, and the include path would be this one here, CUDA runtime, and so on. If we go to the linker configuration, we will also see the linker library set here, and lastly, in the input, we can see the CUDA RT library set here. So in the Unix Linux formatting, it will appear as CUDA-RT, but there is an implied lib prefix here. And this is how is the convention in Linux. So let's try to check where that library is. I'm going to go to user, include user local CUDA targets lib, and here's the guy, lib CUDA RT dot iso is the real file name, but as I have mentioned a while ago, the standard in Unix Linux systems in terms of referring a library, I mean this is a standard how GCC does it, is this lib here is being dropped, and then only the remaining part here, CUDA RT, is specified, such as when you say in the GCC compilation like L pthreads, so you're actually referring to lib pthreads. So you're dropping the first lib and just only specifying the pthreads. So this is just a convention there. So in the input here, this is what CUDA RT here is trying to add as a library. So now that that is set in Visual Studio properties of this project, I can then build this, and the build is happening in the remote target, not in my Visual Studio. So this is the primary, this is how the remote compilation primarily works. Because of the inclusion of the CUDA runtime, we now can access the data structure, that is DEM3 and the CUDA malloc, CUDA memcopy, and stuff. But you will not see here a kernel call of the CUDA, because I wrapped that into I put it into static library here. But the kernel call should be something like, let me go to my system here, helper. And it would look like here. So let us try to copy this kernel function into my project. And let me try to modify the function's name there. Let us try to build this. And it's not building. Let's try to comment outline successively until we find out what's making it not build. Okay, it's accepted. So I guess it's this block IDX, block dim, and thread IDX magic variables is causing it to not build. Okay, yeah. Because when we do this remote compilation here, and it uses the compiler of the remote, it is using the GCC compiler of the remote target here. And the thing here is, once you operate on CUDA constructs, such as kernel call or magic variables of CUDA, such as distread IDX, block dim, and block IDX, these are the magic variables I'm talking about. You would need the NBCC compiler, this guy here. Okay, so in my make file here, I have a full path of that compiler here, this one. This should be the compiler that you would need to use. So because of these impedance mismatch between C, C++, and CUDA extended C++, these two are not compatible. So the C++ has been modified a little bit, extended a little bit to work with CUDA. It is no longer compilable as a C++ source code. Like, for example, this one. When we call the kernel transpose, we wrap it with the triple bracket notation and specifying the dimensions of whose intention here is to express your intent for parallelization of when this function here is executed. So if you want to parallelize that by 1,000 times, 100 times, you have to express that into this additional parameter when you invoke the call, when the rest of these parameter would be the standard parameter of a C++ function call, which will go through here. But here, it be the CUDA parallelization parameter. This is not compatible with C++. This will not compile in C and C++. This will be a syntax error. So what happened is I first compiled this extended C++. Usually it is written in a CU file with CU extension. I usually build this as an object file, and then I introduce it into the main project during the linking stage. And after creating the object file, I converted it to a static library here. See? Okay. And once that is now a static library, I added that into the project here, helper.a, and hence I am now working in a pure C, C++ code base, and I can therefore compile it using a standard compiler. And the linker will be the one in the linking stage, it will be adding the CUDA stuff that we just compiled separately. This is how it's done. This is how it should be done. And I saw how this is done like this in big software. For example, in the dlib open source project, where it has massive C++, but the CUDA constructions are only on very small files, and the remaining C, C++ of the project are in pure C++. It makes the project more portable and compilable on different systems. And through macro preprocessor, you can have the opportunity to have the project build even on systems without CUDA if you can provide alternate implementations. Of course, without the parallel processing as a result. But still, it will make your software more portable and compilable across many systems. And it makes for a good code organization as well. So let me debug this and put a breakpoint. Okay. So during debugging, you just have to be careful not to step over these CUDA API calls. So the way I do this is, as soon as I see these CUDA API calls, let's try with malloc first. Okay, let me press F10 now. Yep. How about this? Let me try again. F10, F10. Okay. Well, in other sessions like the GDB, some of your debug sessions are gonna be broken sometimes. So, well, if you have those kinds of weird behavior during step debugging, you just have to put a breakpoint after all of these CUDA calls and press F5 so that it will pass through these CUDA calls very quickly and the debug flow will not be disrupted. Anyway, so this explains now the simple project that I made in Visual Studio using remote compilation, and I discussed the need for really separating those pieces of code in CUDA that has the extended portion of C++. This part should be separated. The parts that are compatible with C++, such as what we see here, like the call to the declaration of the data structure, yes, it's CUDA, but it's also valid C++. The call to CUDA malloc, yes, it's a CUDA API, but it's still valid C++. These parts can be combined into with the rest of your pure C++ code, as this is still a valid C++ code. But for the rest of the part of the CUDA that are not valid C++, then you should separate it into its own file like this, like the CUDA kernel is not valid C++ because of the presence of these magic variables. And the call to the kernel, like this one, when we are about to call the kernel, this is not valid C++, so we have to separate it, compile it, and once it becomes an object file, a static library file, or a dynamic library, then you have to do the extra step of linking this into your main project, either linking it statically or through dynamic library loading.